Sup guys, welcome to today's show. So today we're going to create our own file system, and I'm going to call mine ddosfs because it's I'm going to use it for my own operating system, which is called ddos. Alright, so let's start by going through some points regarding the specification, because I have to have some limitations since this is my first ever file system. Okay, so one thing will be the max disk size. And the maximum disk size will be around 28 megabytes. And the file system will support around 65,000 files. And each file will have a maximum file size of 64 kilobytes. And this has to do with my operating system. Is 16-bit. And I have designed this file system to be as easy as possible to implement using 16-bit assembly. So that is the most important consideration. And I thought long and hard what I'm going to base this file system, because I want to have some kind of regular file system as kind of a template. And I was considering FAT12, but it has like 15 different constants, and I don't want that in my code. I want it to be as easy as possible to implement, and I want the code to be clean. But after a while, after reading like 15 different specifications, I settled on something which is called simple FS. And the simple FS is in turn based on the Unix file system. So it's a subset of the Unix file system, and it does not have any support for file names or directories, but that I had added to my own file system. And SimpleFS is created by the University of Notre Dame, and I contacted them and obtained a license for this project, and I am extending that license to you. And one more thing, the block size. So the block size is 512 bytes, and that means that everything will be based on that as the smallest atomic part, so to speak. We cannot read or write anything less than 512 bytes. And that's how it's usually done inside of a file system. Always, I would say. But the block size might vary. Alright, so let's go to the actual file system design. So the high-level view of it will be something like this. So there are three different types of blocks, if I zoom in a little bit. So the first block is called the superblock, and that will contain different kinds of metadata for the file system as a whole. Then it follows one or more inode blocks. So when you format this file system, you should set aside around 10% of the entire disk size, rounded upwards, should be inode blocks. So one superblock, one or more inode blocks, 10%, and then the rest will be data blocks. So the data blocks will contain the actual data, and the inode blocks will be divided into different inodes. And inodes is a header which describes one single file. So every file and directory on your file system will have its own inode, which contains the file name and size and where the data blocks are located, and so on and so forth. So this is the high-level view, and this is the same high-level view as the Unix file system has. So everything in Unix is based on inodes, and every file will have its own. All right, so let's zoom in a little bit on the superblock. So the superblock looks something like this. So to the left here, I will type the number of bytes. So as I mentioned, the block size is 512 bytes. So that means the superblock as well will be 512 bytes total. And if we begin at the bottom part of this, so every file system has a so-called magic string. And the magic string is just some predefined bytes, which shows that this is a DDoS file system. So every file system has its own. And mine is going to be a 4-byte string consisting of two 16-bit values. So the first is ddosfs, or DDoS, which is selected just because it looks like the name of my file system. And the second 16-bit word is the following: AA55. And you might recognize this AA55. When the computer is booting, the BIOS will read in the first block or sector from the disk, the first 512 bytes. And it will check if it finds that specific signature, 0xAA55. And if it finds it, it will try to boot from the beginning of that sector. So I have chosen this because using this signature at the end, the BIOS will be able to read this whole superblock, and I will have that in memory by default when I initialize my bootloader, which will make the operating system loading the kernel a little bit easier. Then we have a 2-byte field, which is the total amount of inodes on the disk, and then another 2-byte field, which is the total amount of inode blocks that follow. Because you remember, first we have the superblock, and then we have a couple of inode blocks. So this will contain the number of inode blocks. Then we have another 2-byte field, which is the total amount of blocks on the disk. And then we have 2 bytes which are reserved. So this will initialize to 0000. And these might be used in a future version, but primarily it is because if you look at the how a disk usually is partitioned and formatted, then the first block on the disk will, as I mentioned, contain the magic string AA55, but this part of the disk will contain partition information. But my file system will not allow partitioning. It will need to be a whole disk, and I don't think that's a problem, because either you run one operating system on your machine or you run this inside of a virtual machine. It's not too common any longer to have dual boot and stuff like that. So I will not use partitioning. Instead, I will use this part as the metadata, as my superblock. So that leaves 500 bytes, and this will be reserved for the boot sector code. Alright, so from top to bottom, the first 1 byte field is called the valid/type field. So this contains basically two things. So if we were to look at this as its own field, the last bit, so these are bits and not bytes. The last bit is the valid bit. So if it's 0, it means not valid. So basically that we don't have that file any longer. And if it's a 1, this is a valid inode. So the file is in use. And the rest of the 7 bits are divided as follows. So we have 3 bits, which is in use, and that will tell whether this is a file or a directory. That's the only two things that's supported. So this valid/type field will either be 0x0 if it's not valid. It will be 0x1 if it's a valid file inode, or it will be 0x3 if it's a directory, because we can't use 0x2 because that would make this valid field 0, which means it's not valid. So we can only use odd numbers for the valid. All right, so let's clean this up a little bit. Okay, so let's continue. The second field is a 2 byte field, which is the size in bytes. So that's the actual file size, or it might be 0 for a directory. Then comes an 11 byte field, which is this can be a directory name as well. And the file name will be organized in 8 for the first part, and then an extension of 3. Alright, so then the rest of this inode is so-called pointers. And that's not the kind of pointers that you're used to if you are coding C, for instance. But I'm gonna show you in a little bit. So there are 2 fields here. The first one is 2 byte large, and this is the indirect pointer. So basically this will contain the block ID of another block. So if we were to visualize it like this, so this is a data block somewhere on the disk, and this indirect pointer contains the ID of this data block. So when we index into the disk and load a specific block, that index will be used, which is found inside of this indirect pointer field. And this in turn contains 256 2-byte pointers pointing towards other blocks. So if this is a directory, this could point to different inodes, making up the directory structure. But if this is a regular data file, it will point to different blocks, different data blocks on disk. And then we have the rest of this is the direct pointers. So we have 8 of those, and they will in turn point directly to a data block. So this means that all small files, so up to 4K, will be directly pointed and a little bit faster to access. And if the file is bigger than that, it will also populate this indirect pointer field, which makes it possible to have bigger files. So the only limitation is basically the size field right here. Since it's a 2-byte field, it will be 65,000 different combinations, and thus 64K approximately in size. All right, so this might be quite a lot, but if we were to repeat some of that, so the high-level view, everything is divided either in the superblock, and there's one of those, and then 10% of the disk are inode blocks containing the inodes, one per file or directory. And then the rest is regular data blocks containing the file contents. So then we have the superblock, which the first 500 bytes are reserved for the boot sector. And we have an additional field which is reserved. And then we have the number of total blocks on the disk. We have the number of inode blocks, the number of inodes inside of these inode blocks, and the magic string, which is ddosfs AA55 in hex. And the block size, as I mentioned, 512 bytes. And that's, nowadays, most file systems use a 4K block size, but that is not necessarily supported inside of the BIOS when using 16-bit assembly. So it makes things a little bit easier to code if it's 512 bytes. And then we have the actual inodes containing a valid/type field, which describes if the block is if the inode is in use, and if this is a file or a directory. And then we have the size in bytes, and we have a file name consisting of a string up to 8 characters with an extension up to 3 characters and a dot in between. The dot will not be saved inside of this structure though. Then we have indirect pointer, which points to a data block which is being used for 256 2-byte pointers. And if we're talking about files, these pointers will point to different blocks. So the index of the block on disk. And if this is a directory, it will contain the inode. And then we have direct pointers, 8 of them, which point directly to different data blocks. Alright, so while I'm developing my operating system, I will be using an extra layer, which is the API layer. That makes it possible to run the shell and things connected to that during development on top of your regular operating system. So that means I will also need to create a disk emulator, which will, instead of using the regular disk, it will use a file on your file system, and it will treat that as a disk. So the disk emulator will have a structure which looks something like this. Alright, so it will have a 32-bit field for the file descriptor, and that will be the file descriptor for that file on the disk that is emulating the actual disk. And we will have an int16, which is the total number of blocks, a boolean, which is called attached, which says if the disk is attached or not. So that's similar to if it's mounted, but on the actual disk layer, because if it's mounted or not is at the file system layer, but this is if the file on disk is open, basically. And then we will have a drive number, an int8. So I haven't yet decided, but I think I'm gonna do something like 0 will be the C colon drive, 1 will be the D colon, and so on and so forth. Possibly I will do so it's 0x80 at C if I want to support other things like floppy drives. This is a better system, but I haven't yet decided. Alright, so this is the structure, and it will be pretty simple, the API for the disk emulator layer. Basically, we will just have something like this. I will have a function which is called attach, and the attach function will take in the drive number as input, and it will provide one of these structures as an output if it's successful. And I will also have a detach function which does the opposite, and I will prefix these with a D to indicate that these are disk operations. Similarly, I will have a disk read and a disk write. And it will take in the block number as the input, and also a memory address, so where it's gonna read the data into and where it's gonna write the data from. So it will read and write a single 512 byte block. And this is it. This is all we need for the disk emulator layer. And when we go into production with the operating system, there will not be a disk emulator. Instead, these will simply be BIOS system calls. Or probably, it will be system calls inside of my operating system, interfacing with the BIOS. All right, simple enough. And the last thing will be the file system API. So if we take a look at the data structure for the file system, it will look something like this. Alright, so it will look something like this. First we need the drive number, so we know if this is the C colon drive or the D colon, etc. Then we will need to have a disk descriptor, which is the struct from this page. So this is what is returned from the attach function. Then we will have a bitmap. So this will be an array of booleans which will contain one boolean per block on the disk. So if it's true, the block is in use, and if it's false, the block is not in use. So we can use this to in an easy enough kind of way, locate blocks that we can use. We will also have a copy of the superblock, which will be the metadata, so we always know all the different things which is contained inside of the superblock structure. And that's basically what I showed you from the beginning. So the number of blocks, the inode blocks, inodes, and possibly even a copy of the magic string. All right. And this we can set inside of parentheses. I haven't yet decided, but it would be beneficiary in some occasions if we were to have a copy of the root directory for easy access. But it would still be problematic if we needed to make changes, because then we need to have two different sources of truth. So I haven't yet decided about that one. By the way, the root directory will be found because it will have the first inode. So inode 1 is the root directory. Yes, so that is the file structure, and that will be returned when we mount the file system. And then we will have a lot of different functions. I can mention a few of them at least. We will have something called fs create, which will create a file, an inode. And we will have an fs destroy, which will delete an inode. We will of course have fsread and fswrite, and that will probably be the most tricky part of this implementation, because the disk layer will only read and write specific blocks, but the fsread and fswrite will read and write one single byte each. So we need to figure out the offset into that block. And then we will also need to have a function named fsformat, which will be formatting the disk drive. And I will also make some kind of utility program which we can use to format, and it will provide two different functions. Either it can format the disk so that the reserved boot sector is all zeros, which will constitute an extra drive, like a D: drive or something like that. Or it can be bootable, which means it will write the bootloader. So in that case, it will take an argument with that bootloader file. So a 500 byte binary file. And then we'll probably need some kind of show function which will print some information about the disk, which will be very useful when developing. So it will go through the disk and print information from the superblock, and it will for each block print, or for each inode at least, print out the information from that structure. Possibly I will also create some kind of fsstat function which will return some information like about a file or something like that. And of course we need to have fsmount, which will mount a disk. And I think I'm gonna do it so when we mount the disk, it will scan through every block on the disk, and it will create the bitmap. I think I'm gonna do it like that. Possibly I will do it so we create it when we format the disk and we store it on the disk, and we write it when we unmount the disk instead. That will be a little bit more efficient, but I don't want to make this implementation more difficult than I have to. So we'll see. But this is the first file system I have ever constructed, and I hope most of this will work. Possibly I will make some changes along the way. But this is the general idea anyway, and I intend to create something similar to an RFC detailing this specification, and I intend to release this file system under an MIT license. So most of my operating system will have my regular Birch license, but this file system part of it will be MIT. So you can use it for whatever you want. I think that's it. So in the next episode, we're going to start developing this, and hopefully the entire disk emulator can be created in one episode. and then we will take care of the file system API. And the lower level stuff we will do when we start building our kernel. So I hope you liked this episode and want to continue the series. Please like and subscribe, and don't forget to hit the bell icon if you want to have a notification when I drop the next episode. So thanks for watching, and thanks for today. Did you know that I made a book about computer networking? You will learn how the internet works and how everything works under the hood. It's a complete beginner's course, but it has some advanced elements as well. And you will learn network design and network security and all different kinds of stuff. For more info, check out books.drbirch.com. That is books.drbirch.com. Thank you for your support.